day 4, and they start on page 13 of your packet. I recommend colored pencils. I do a lot of color coding in these notes. So these notes are, we're going to talk about the area of a region between two curves. And so we know that when we integrate that definite integral, the value of that definite integral defines a region that's between the function and the horizontal axis. So we're going to adapt that in this set of notes, and we're going to see how we can use integration to find the area between two curves and not involve the horizontal axis at all. So this isn't in your notes, but just kind of be an active listener and an active thinker here as we kind of go through this concept. So we have a function here. I just made the function completely positive. And we know that the definition of this definite integral would be to start at A and sweep to B. So A is on the left, B is on the right. And as we sweep across this region, and as we do the appropriate integration to f of x, we get an area, we get a number that represents the area of this region. And so we know that we can call it the area under the curve kind of really loosely, but really by definition, it's the area between the function and the horizontal axis in this domain. So the question is then, if we introduce a second curve, how can we find the area between those two curves and not have to worry about this whole horizontal axis thing? And so let's extend that. So let's bring back that same function. Positive, it's all positive, but that doesn't really matter. And we'll explain why in just a little bit. You might want to hold off and take these notes after pausing the video, just to kind of take it all in and think about it as we're talking about this. So here's our f of x. Now I want to introduce a g of x, and my g of x that I'm going to introduce is this function here. Notice it goes across the same domain, and so and it has this area here between its function and the horizontal axis. And so if I superimpose these two curves, I can generate a region between f of x and between g of x, and between f of x and g of x. And so that's the number I really want. And so I want really just this visible green region, not the stuff behind the red. And so this might be pretty intuitive as to how you might get this answer. So if I want just this region, then what I can really do is integrate to find the green region and just subtract out the red region. And so we can fit that, since we're going through the same limits of integration, we can fit that all into one integrand and just subtract the two functions. And that's effectively subtracting the red area from that green area that goes all the way down to the horizontal axis. And the nice thing about this, this adaptation is that here's my same function that I started with, f of x, is that even if I have a g of x that has a negative value, so if you think about that and I superimpose these, I'm not going to do it quite yet, but if you can picture these being superimposed, then I have a region that's green plus red. But I don't have to change this. I can still stick with this, this formula here, so to speak, this adaptation, because this region would come up as a negative region when we integrate it anyway. So minus a negative is a positive. And so it's like physically adding green plus red to get blue. So this adaptation still works, because even if this function is negative, subtracting the negative is like adding. And so I'm adding those two regions together by using this notation. So that's the really cool thing, is that this notation works no matter where the curves are. If the curves are positive or negative, it just doesn't matter. Just stick with this adaptation and you'll be good. So let's talk a little bit about what's happening now. So I've color coded this, like I said. And so blue represents the area of the region with the value of the definite integral. And the black are the limits of integration. We're going from A to B, so we're sweeping to the right. F of x is green. That represents my bigger curve. So it's the curve that's on top. It has bigger y values. And g of x is the curve that's below. So it has smaller y values. And so this is the adaptation to just a plain old integration with one integrand that we can use to find the area between two curves. This answer is always going to be positive because we're taking a top minus a bottom, or a big minus a little, which is always going to result in a positive answer. And we know from geometry that area is always positive. And so what makes this work? Well, what makes this work is that f of x is better than g of x. So this is always going to result in a positive value. The limits of integration are the same. We're going from a to b across f of x and g of x, and the functions don't cross. So think about it. If g of x came up above f of x and they crossed, maybe in the middle here, then g of x would then be on top. So it would be the bigger function. So that would require two integrals from a to the point of intersection, and then from the point of intersection to b. So it gets to be a multiple integral problem when they cross, and that's something for another day. Okay, so you might want to pause the video now and take these notes down at the top of your notes with the color coding. If you have the appropriate color pencils, you can just stick with the green, red, and blue. Otherwise, make up your own color coding. Okay, so if you're started up the video again, I'm assuming that you've got these notes down at the top of your notes. So I'm going to talk about what happens here. So notice this blue area disappeared. So I want to talk about what's happening with respect to these scenarios where f of x with why it makes it work. So as we're sweeping this area across, I just want to reinforce that. Notice that as we sweep across like that, the green function f of x is always above the lower function g of x. So again, we got no crossing here. So and that's what that has to be the case in order for the integrand to be positive. So that is definitely a really important concept there. Okay, so going on, let's try this problem now. I've got kind of a strategy here listed, and this is a real general strategy. Well, like I said, it's a real general strategy. This will apply for any area of problem. Okay, so let's take a look at example 1. Finding the area of the region bounded by the graphs x squared plus 3 and y equals x from 0 to 2. So this looks a lot like our example here. We've got a curve on the top, we've got a curve on the bottom, and we're just kind of chopping it from 0 to 2. Okay, so we sketch the curves, we've got them sketched here. This is the answer. We're just going to check our answer as we get it. It says find the points of intersection, if any. So these two curves don't have any points of intersection, and we can see that visually. We could set these equal to each other, and when we set these equal to each other, there would be no value of x that would solve that. It would be unfactorable, so to speak. So we will have to do that eventually, but we won't have to in this example. So we need to write expressions for the area, and then we have to identify the limits of integration and integrate and evaluate. So the area then is going to be this top curve minus the bottom curve. So I look at this and I think of parabola minus line. So parabola minus line. So there's my parabola, there's my line, and so it looks like that, top curve minus bottom curve. Identify your limits of integration. So in this case, I'm going to go from 0 to 2, parabola minus line, and then we can go ahead and integrate and evaluate. So this type of problem would be definitely a no calculator problem. So let's go ahead and do the antiderivative. So x cubed divided by 3, we've got plus 3x, and then we've got minus x squared over 2. And then we can plug in our limits of integration. So we're going to plug in 2. Oops. We're going to plug in, there we go, we're going to plug in 2, and then we're going to subtract and plug in 0. Now, keep in mind, this is an answer. So once you have it to this point, you don't have to evaluate it. We know it equals 6 2/3. So if it's a no calculator problem, leave it like this. The grader grades this. As long as your 2's are in the right spot and your 0's are in the right spot and all your integration is correct, they count that as a correct answer. Mathematically ends up to be 40 divided by 6, which is 6 2/3. Okay, let's look at this next example. So this next example, Again, it's we've got a top curve minus a bottom curve, and it says let R be the shaded region. So this is shaded here in bluish, sort of, in the first quadrant, and it's enclosed by the y-axis, so the vertical axis, and the graphs of sine of x and cosine of x. Just find the area of R. So the first thing we need to know is which is the big curve and which is the little curve. So if this is a no calculator problem, you have to know what sine of x and cosine of x look like close to 0, so that you can determine which is on top and which is on the bottom. So if you remember, cosine is 1 when x is equal to 0, so the blue curve must be cosine, and the orange curve must be sine. Okay, so I also want to talk about this scenario, because this is common. I would say example 1, they would probably not ask you this question, but when they start introducing trigonometric functions or more complicated functions, a lot of times they ask you to set up but do not solve. So in other words, they want you to just, I'm just going to back up here, they want you to just set up. So they want you just to write this expression and then go on. They don't want you to solve it. So that happens a lot when we get to more complex expressions. So we'll talk about that as we approach that. So we know the cosine is the bigger function, sine is the littler function. So we need to find this point of intersection without a calculator, because we know that we're enclosing this, which means it starts here on the y-axis and it ends here wherever they cross. And wherever they cross is where the values are equal. So you have to know enough about the unit circle to realize that the cosine and sine have the same value when x is pi over 4. And that represents then our upper bound, our right-hand side of the shape. So to set this up then, our area becomes 0 to pi over 4, cosine x minus sine x dx. So that's that. If this question were set up but do not solve to give me an expression for the area of region R, you would stop here. So what do you need to have to get all the points? Well, you need to have an appropriate integrand. So you got to have cosine minus sine. You can't have the other way around. You've got to have the appropriate limits of integration. You have to have an integral symbol, and you have to have a dx. And so this is usually a 3-point graded question where the integrand is worth a point, the limits are worth a point, and having an integration symbol and a dx is worth a point. So that's how they would create set up and do not solve. But this example says we need to find the area, so we need to solve this. So we know that the antiderivative of cosine is sine, and we know the antiderivative of sine is minus cosine. So if this is the antiderivative is minus cosine, and we have a minus here, then we have a plus cosine after we integrate, and then we have to evaluate that from 0 to pi over 4. Okay, so plugging in pi over 4 looks like that. And then plugging in 0, we're going to subtract and plug in 0. And this is, this is, you know, we gotta really be cognizant of the fact that this whole thing in the right brackets is not 0. This is 0, but this is 1. So often students say, oh, I see zeros here and this whole thing's 0. That's not true. So we have root 2 over 2 plus root 2 over 2. So root 2 over 2 plus root 2 over 2 is the square root of 2. And then we have minus 1. So that's your answer, square root of 2 minus 1. And we know square root of 2 is 1.414 something. So if we subtract 1, we have about 0.41. We don't have enough digits here for an acceptable answer for College Board, but that gives you a good estimate. Again, though, if this were a no calculator problem, this step above here after we've substituted in pi over 4, that's a numeric answer. So you could stop here. You don't have to give the answer in this form. So that's especially useful with trig functions if you really don't know the unit circle that well. That's a great strategy. All right, so now we're going to switch gears because the model we have works really good when f of x is on top, g of x is on the bottom, and they don't ever crisscross. And this is not that case. If you notice, I'm going to take away the region for just a second here. As we sweep from left to right through this region, we have red on the top and red on the bottom. And we can do that. That's just a positive square root minus a negative square root. But at this location, we introduce a new function. So as we sweep from 2 to 8, now the red is on the top and the green, the line is on the bottom. So if we use a dx, if we sweep from left to right, so sweeping from left to right is a dx problem. If we use a dx approach, then we have to divide this into two expressions. From 0 to 2, we have the positive square root minus the negative square root. And then from 2 to 8, we have the positive square root minus the line. And we can do that. That will get us the right answer. But this is really labor intensive. So we're going to kind of set this aside here and look at this a little bit differently. If we start at the bottom and sweep to the top, so this enclosed region starts at -2 and it ends at +4. If we sweep from the bottom to the top, then the green function, let me back that up, the green function is always on the right-hand side, and the red function is always on the left-hand side. And that's equivalent to what we were doing before, where f of x is always on top and g of x is always on the bottom. Now, f of x is always to the right, and g of x is always to the left. So we can start at -2 and go to 4. And we can take the right-hand function, but we're going to write it in terms of y, because these are all the right-hand x values, and these are all the left side x values. And so we can take those right side x values and subtract the left side x values, which means rearranging these so that we have x equals. This one's already in that form. And then we can do this with one integration, because those things never change positions. So if this is function f of y and this is function g of y, then if we want to, this is effectively just rotating it 90 degrees. And if we just rotate it 90 degrees, then we can write this all in terms of y. And then this, like if we just spin this counterclockwise, the f of y would always be on top and the g of y would always be on the bottom. So we still have effectively top minus bottom. It's just realistically it's right minus left. And of course, if these are x values, if the ones that are farther to the right are bigger than the ones that are to the left. And so what that means then is that the line, if we solve this for x equals, we'd add 4 both sides. So we're going to go from -2 to 4. And we're going to have y plus 4. Excuse me, that should be a plus. Okay, typo. Let me stop here. We have y plus 4. Just get back to that point. There we go. Solving this for x, we add 4 to both sides. We have y plus 4. And then we subtract the half y squared and integrate that. And we integrate that from -2 to 4. So from the bottom of the shape to the top of the shape. So this is literally just rotating everything 90 degrees. We're going from bottom to top instead of left to right. We're saying right minus left instead of top minus bottom. It's a rotation of 90 degrees. Now, I would say that this one would also be a valid no calculator. The integration of these things is not that bad. But let's go ahead and do the integration on the calculator instead, just for time's sake. So I'm going to do a math 9, and I'm going to go from -2 to 4. And I want to point out that I'm literally treating this like an x problem. I'm going to put in x plus 4, because x is my variable key on my calculator. Now, hold on here, because I really should practice good structure here. So I'm going to insert a bracket because I have x plus 4 as that first first function. I always want to put those in brackets. Minus, and then new function. New function is half y. So I'm going to say 0.5y squared. So 0.5x squared. So literally look at this. I'm going to put that in its own brackets. We're going to integrate with respect to the variable of integration on my calculator, which is x. So notice that my calculator, I plug in my variable key, which is x. That represents all the y's. It'll work out to the right answer. This is just these are just dummy variables. Doesn't matter what they are. Okay, so hitting enter, the answer for the area between these two curves is 18. So that answer is 18. This, if you want to try it on your calculator, dividing it up into 2 and sticking with the dx's, also works out to be 18. You can check that on your own time if you'd like to. So here's a really common problem. This is how we get a lot of bang for our buck in free response questions. So we have 2 curves and we have 2 regions. And so this is how they can test a multitude of strategies in one question. So we have regions R and S in the first quadrant, and region R is bounded by the x-axis and the graph of 2x cubed and tan x. So, and they've identified them for you. Here's 2x cubed, 2 minus x cubed, excuse me, I said that wrong, and tan x. Region S is bounded by the y-axis and the graphs of 2x cubed and tan x. And it says find the area of region S and find the area of region R. Okay, so let's look at region S first, because that's our dx problem. So we know these are identified. I'm going to put them green and red for top curve and bottom curve, and we're looking at region S. So if we take that information off, if we want to integrate region S from left to right, we know it starts at 0 and ends at this point of intersection, and we need to find that point of intersection. So that is going to involve graphing these two on our graphing calculator. This is a calculator question, right? It's got a little calculator there. So we are going to graph 2 minus x cubed. So caret 3, there we go. And then we're going to graph tan x. There we go. We're just going to check our mode real quick, make sure we're in radian mode, right? I always am, because I just do calculus, I don't do physics. But you might be, so you might have to switch to radian mode. Okay, so there are my 2 functions. I'm going to take my clues from the graph here and just graph this first quadrant. We know that this if we go out to 2, then we've gone, even if we go out to 2, yeah, let's go out to 2, then we're way in the negatives here. So I'm going to adjust my window here, and let's see what else we know. This crosses, what is this? This crosses at 2. So I'm going to come up here to maybe 3 and go out to 2. That's what I'm going to do for my window. So my x min, I'll stay at 0, and I'll come out to 2. And my y min, I'll stay at 0. And what did I say, 3? Okay, so excuse the announcements here. All right, so now I'm going to go back to the graph, and I'll go back to the light. Okay, so here's my graph. So it looks kind of like what you see in the graph here. In fact, I'm going to go back here just for color coding. I am going to. Yikes, that was a long announcement. I'm going to, let's see here, let's go to green. Okay. And let's go down here and make this red. Oh, that was a long announcement. There we go. Okay, now it'll look much more like what we have in the problem. There we go. Okay, so we need to find this point of intersection. So we're going to do a second and calc and intersect. Second calc 5. And we need this intersection. So my first curve, notice it's blinking on the green curve. So I'm going to hit enter. And my second curve is red. I'm going to hit enter. And I'll back up a little bit closer to this intersection just for the guess. And so we have this intersection of 0.902155. and 1.2657507. Okay, so that is this ordered pair. So notice what I'm doing here. This is obviously a calculator problem, so we just find this just as I did. But I'm labeling it A comma B, A comma B. And because these decimals are long, I'm not going to try to write them each time. I have to write an integration. I'm just going to use the A and the B as the upper and lower bounds. So this is how this makes it a little more streamlined and a little more efficient. So we're sweeping from left to right, which means we're going from 0 to this x coordinate. And this x coordinate is 0.902155, but I'm just going to call it A. And I've defined it. This is the important part. I've defined it in the problem as A, so I can use A. So when I write this, here's my general expression, right? When I write it pertaining to the variables and the functions in the problem, I'm going from 0 to A. And then my top curve is my cubic, and my bottom curve is my tan, and that's my setup. And so now I have to put this in. So this is the other thing that's really, this is as much a exercise in graphing calculator, learning some efficient moves here, as it is calculus. I'm going to use these y1 and y2s so that I don't have to type this stuff all the time. Okay, so what I'm going to do, well, actually what I'm going to do is I'm going to go back to the graph, and I'm going to find the area of this region. Now, if I did an integration, it would give me all the way down to the bottom. So I don't want to use my second calc integrate. I really don't want to use that because I can only put in one function, and I need to put in two functions. So I'm going to have to go back to my math screen and do a math 9. And I start at 0 and I end at that coordinate A. This is where I have to type it in, unfortunately. So 0.902155. So 0.902155. But now I'm going to grab y1 and y2, and that's under your vars key. Your vars key is next to the clear key. So vars, y vars, function, and I'm going to grab y1. And then I'm going to hit my minus and do the same thing for y2. Vars, arrow over to y vars, select option 1, function, arrow down to y2, and hit enter. And so that's the same as typing in the functions, because the functions are located in y1 and y2. Hit my variable key x, because these functions are in terms of x in the graphing mode, and then hit enter. So this is 1.160. Now we have to decide, do we want to write a 0? We could. It's appropriately truncated. We could round this to a 1 because of this 5 here. That would be correct. Or we could keep this as 1.605, and we could list any of these digits as long as they're correct. So I'm going to round. I'm going to say 1.161. So that is the answer for that region. Okay, so now we're going to do region R. Region R is down below here. And if we sweep from left to right, notice we switch from red to green. And if we switch functions, we're going to need two integrands, which we can do because we have that point of intersection. We can go from 0 to 0.902155, and then we could go from 0.902155 to 1.2657551. You know, we can split it from this and just do the red curve and the green curve appropriately. But we can also sweep from bottom to top, which changed it to our dy question. So if we sweep from bottom to top, then if we can spin that counterclockwise 90 degrees, the green is the big function, the red is the little function. So it looks like this. Bottom to top means I start at 0 and go to this y coordinate, which is b. And again, since I've defined b to be 1.265751, I can use b in my notation. And then I've got to solve each of these things for x. So solving this for x involves relocating the y and the x cubed. And so this is the cube root of 2 minus y. And then solving this for x involves taking the inverse tangent. So this is the inverse tangent of y. And now let's go ahead and do that in our calculator. So I don't have those functions. I can't use the vars here. So I'm going to just do a math 9 from 0 to the y coordinate, which is 1.265751. 1.265751. And then I have the cubed root. So cubed root, we actually do have a cubed root under math. It's right down here if you want to use it. And then we're going to write, what is that? Cube root of 2 minus y, 2 minus y, but remember our variable key is x. And I'm going to close that bracket, and then I'm going to subtract inverse tan. So second tan variable. There we go. And I could have an extra set of brackets around that too. It could look like this, which is not a bad idea. There we go. And so each has its own set of brackets. And then the variable of integration on a calculator is x. And I get 0.729. And that would be the correct answer. And then any digits after it would be fine as long as they were correct. So that answer is 0.729 for that area. Now, a quick comment here. If this was a setup and do not solve, then you would stop right here for part A. Oops, accidentally clicked. You'd stop right here for part A, and you'd stop right here for part B. Okay, so just to kind of give you an idea about that. Okay, so when we get into the classroom, we'll go through the takeaways. There's going to be more takeaways here and address any questions you might have regarding integration.